working? Yep, it's recording. All right, so what we'll do today is to basically finish all the topics here. Then we'll be ready to talk about, move on to the next section. Okay. We have already talked about some of these topics, like expressions, conditions, expressions, compound statements, basically a block using the open curly brace and closed curly brace, and the conditional statements. So last time I think we stopped, with conditional statement. I gave you guys, an example of, how without the use of curly braces, things can get really messy. Okay, it doesn't do what it is supposed to. That's the worst part. Okay, the worst part is if you look at the indentation of the code that we talked about last time, it suggests that it is nested in a particular way. But the way the compiler works is it will nest it in a slightly different way. It is not syntactically incorrect, which is the biggest problem. If it is syntactically incorrect, at least the compiler will catch it and say, cannot process it. Then you're forced to look at your code and go like, okay, what's wrong with this? But it's syntactically correct. And using the indentation, it looks okay to you. It looks like, it should be nested in a particular way, but the compiler sees it differently. Okay? And to me, that is really one of the worst kind of problems that you can have, is the tool cannot check it. You look at it, it looks good, except the compiler looks at it in a different way and interpret it differently. So that's why you have to use, that's why you don't have to, but that's why I recommend that you use open curly brace and closed curly brace as much as possible to help you clarify what is inside of what else. So let me just kind of point you to the part that I'm talking about here. So I'm talking about, stuff like this, and, this part is, how I would write the code initially is to write the template first, and then we'll go back and fill in, what you need to do when a particular condition is true. So this is what we talked about last time. The example that I used in class is different from this one, but nonetheless it goes, it talks about the same point. Are there any questions regarding, what we talked about on last Wednesday? I know it's been like 5 days, but are there any questions related to all that stuff? Okay, I'm not expecting everyone to feel comfortable reading C code as if you're the compiler, okay, because that really takes quite a bit of experience and training. But the use of not parentheses but curly braces really help to visualize, what is nested within what else. So even when it is not needed, I still recommend that you use it just to emphasize, okay, this is the opening, this is the close, and whatever is inside this particular construct. Are there any questions about all that stuff, the curly braces and how to read a conditional statement? Questions? Okay, so if there are no questions about conditional statements, we are now moving on to talk about loops. Okay, there are basically two main types of loops, and one is a shorthand of the other one. The third one is a shorthand of the first one. So we'll talk about all three today. Instead of just talking about what is a pre-checking loop and what it does, I'm going to show you some examples and basically point out some of the kind of important things that you cannot get just by looking at the syntax of a while loop. So we'll start with what I call a pre-checking loop and what most other people call a while loop. The reason why I call this a pre-checking loop is because the condition is checked first. Okay? And then if the condition is true, then you go ahead and execute whatever you specify as the body of the loop. And once you're done with the body of the loop, you go back to check the condition again. Okay? So we'll go ahead and take a look at the basic syntax. The basic syntax of a while loop looks like this. It is the word while, W-H-I-L-E, open parenthesis, and inside the parentheses you have to specify a condition. And that condition is basically a Boolean expression. Non-zero means true, 0 means false. And then a close parenthesis. As with a conditional statement, whatever statement after that is the body, quote-unquote, body of the loop. You can use any statement. Okay, you can use a simple assignment statement if you want to, or you can use a curly brace, closed curly brace to make it a block. I recommend using open and closed curly brace. We talked about it many times already, but I would recommend doing that just because it is more general, and you don't have to worry when you need to expand the logic inside that particular block. And this expression, if it is evaluated to be true, it will execute whatever statement that is here, and then it will go back to reevaluate the expression. This is the main difference between a conditional statement and a loop. With a conditional statement, it will do it once, and then it goes on to whatever is after the conditional statement. With a loop, it goes back to reevaluate the condition. If the condition is still true, it will continue to do the statement and then go back and recheck the condition. So do we have any questions about the general idea of a while loop? A pre-checking loop? In your previous class in CISP 300, 301, or 370, it doesn't matter who you take it from, you should have some exposure to pre-checking loops already. Okay, is that okay? All right. So next thing we'll do is we'll take a look at a test program. Okay, we'll just go ahead and take a look at a test program and see what type of while program we can write here, a while code. So I'll call this the while6.cpp. I'm not going to reuse the programs that I wrote this morning. All right. So we'll start with something that is not tricky at all. Okay, so this is basically as plain as you can get to illustrate, how a while loop works. So in this case, we have, oh, I forgot one thing. Okay, x gets initialized to 0, and then we have a loop while x is less than 5, perform whatever is inside the block statement. In this case, I do not really need the open or close curly brace in the inside because I only got one thing to do. In other words, if I were to write this program like this, it would have done exactly the same thing. It would have meant exactly the same thing. It's just that if I need to add something to it, for instance, if I have to track something else, like I don't really know what it is, and I can say, oh, you know what? Before I add one to x, I also want y to be, incremented by, the amount of x. Okay. That is misleading. It is not syntactically incorrect assuming y is a variable. This is not syntactically incorrect, but the loop is only consisting of that line, y gets y plus x. X gets x plus 1 is no longer a part of the loop because the while statement is expecting only one single statement to be its body. Now it has got, x gets x plus, y gets y plus x, and it pushes the other statement to be outside of the loop. So in this case, this becomes an infinite loop because assuming x is less than 5 to begin with, it will always be less than 5 because nothing in the loop is changing x. Okay, but syntactically, it seems to suggest that x is incremented in the loop. It is a part of the loop, but it's not. Okay, so that's why I don't do it this way. Instead, I always use curly braces to enclose what I need to do in the loop. Okay, let's try to answer a few questions before I even run this through the debugger. What is the value of 5? Okay, 5 is the answer. I was about to ask what is the value of x when we get to the return statement, and the answer is 5. Okay, because in this case. Now you can kind of analyze why that is the case. If I were to ask you why that is the case, instead of saying, yeah, we traced the program, we ran it through the debugger, and x has a value of 5 by the time we get to the return statement, you can kind of reason it out, right? Because x gets initialized to 0, and then the only other statement that can change x is x gets x plus 1. Okay, so every time we change x, it would be 1 more than before. So that means, when we're in the loop, it will go from 1 to 2, 2 to 3, and so on. So now the question is, when are we getting out of the loop? We get out of the loop not when x equals 5, but when x is greater than or equal to 5. Okay, so you have to make that statement as general as possible. Okay, so we get out of the loop when x is greater than or equal to 5, but since we're only adding 1 to x sequentially, it will have to get to 5 first before it get to any number greater than 5. So that's why by the time we get out of the loop, it would have a value of exactly 5. Okay, so that's what I claim this program would do. And next, we'll go ahead and test it just to find out whether it is doing what it is supposed to. So we'll go ahead and compile the program first. This is while 6. And use GDB to basically run the program one line at a time. So we'll go ahead and put a breakpoint on line 6. Okay, so every time we get to line 6, it will stop before the condition is evaluated. And line 6 is interesting because sometimes, most of the time, it will go to line 8, and one time, throughout the execution of this program, it will get to line 10 to exit the loop. So we'll go ahead and take a look. Basically, it's not really mysterious. Okay, x has a value of 0 to begin with. We continue execution. Well, let's single step, and you can see it goes to line 8. Okay, not a mystery. X would still have a value of 2 because, of 0 because this is before line 8 executes. When we single step, where do we think we should go? I'm at line 8 right now, so if I single step, which line should I go to?
6.
Line 6, exactly. We go back and check the condition again. Okay, so we are now back to line 6. X has a value of 1. Single step, we go to line 8 because 1 is less than 5 is true, so we have to perform line 8 here. Single step again, line 6, line 8, line 6, line 8. So let's check. X now has a value of 3 before line 8 executes. Now x has a value of 4. 4 is less than 5 is still true. We have to go back to line 8 one last time. This time, after line 8, x has a value of 5. Double check. And if I single step, it should go to line 10 and not line 8 anymore because 5 is less than 5 is false, so we are getting out of this loop. So now we get to line 10. Nothing unexpected. Everything is pretty much, really standard. Okay. All right, so we'll go ahead and copy this program. So I'm copying while 6 to while 7. And we'll make a very simple change to this program, and you can tell me what this program is going to do. Okay. I changed the way I initialize variable x. So what do you think this program should do?
It'll go to line 6, and then it'll go to line 10.
Yep. It will go to line 6 and then skip over the whole thing and then get to line 10, because as a pre-checking loop, it is possible that you may not even perform one single iteration. Okay. So once again, let's go ahead and check it. Debug it. All right, list the program. Once again, we put a breakpoint on line 6. Run the program from the beginning. Print the value of x. This is the first time we get to line 6, but because of the way we initialize the loop, the way we initialize x, x already has a value of 5. 5 is less than 5 is false. This is the first time we evaluate the expression, but it is false already. So when we single step, it would not go to line 8. Instead, it will exit the loop and get to line 10 directly. So is that okay so far? Okay. All right. So what else can we do with this program and make it tricky? Make it even more tricky.
Not initialize x.
Well, let's see. Let's do something that has to do with what we have learned in the previous few classes and combine it here. So we'll do something along this line. So I do not have x gets x plus 1 in the loop anymore. The quote-unquote body of the loop is now empty. There's nothing to do inside the body of the loop. But instead, the increment of x is moved into the condition itself and using a post-increment operator. In other words, the comparison is using the value of x prior to the increment. But the side effect of the expression is it will increment x anyway. But we are not going to use the post-increment value for the comparison. We're using the pre-increment value for the comparison. So that means the first time we get to line, okay, let me just turn on the line number here. So the first time we get to line 6, the value that we are comparing against 5 is not 1, it is 0, because x was initialized to 0. But then by the time we get to the quote-unquote body of the loop, which is empty in this case, x would have a value of 1. Okay, because it's post-increment, so that means, even though we don't use the incremented value for comparison, it will increment the value of the variable. Okay, so in this case, by the time we get to line 9, which is the return statement, what would be the value of x? This time, yeah, go ahead.
Yeah, 6.
It will be 6, okay? The reason why it is 6 and not 5 is because when x gets to 5, okay, 5 is less than 5 is false, and then we get out of the loop. However, we are using the value of x prior to the increment. So prior to the increment, it already has a value of 5, so the increment will turn that into, will increment 5 to 6. So by the time we get to line 9, x ends up with a value of 6 already. Okay. So let's check that, okay? So we'll double check, make sure that that really is the case. So we put a breakpoint on line 6 and run the program. And this time I'll just, oh, I cannot continue. It optimized itself to the point where I cannot put a breakpoint and stop it with each iteration. So I can put a breakpoint on line 9, run the program. It kept the breakpoint on line 6, but I can't really single step it. It just did all the iterations and ended up on line 9 in this case. So x does have a value of 6 by the time we get to line 9. Yeah.
So by doing that, does that have any effect on the code? Since in debugger we can't step through it, we had it written out the long way.
The reason why we cannot step through it is because there's no code in the loop to stop at. There's nothing to stop at.
Okay.
The empty statement, even though it looks like open curly brace and close curly brace to us, plenty of place to sit to basically put a breakpoint on, it doesn't generate any actual code.
Okay.
So, and that's the reason why you should use open curly brace and close curly brace whenever you feel that the extra notation is needed, because it doesn't generate any extra code. It's not making your program running any slower. But in this case, it's not convenient because I cannot stop and show you that it's actually
Could you tell
going
it to
through.
print in the brackets then?
Yeah, you can make it. Sorry.
Could you tell it to print in the brackets then? Like when it gets to the line, just command it to print.
Yeah, you can make it print and do something, so I can put
So
a
you could
breakpoint
see
there.
it or something.
You can do that. So to do that, we'll have to do a count include stdio. And I'm just printing the value of x here. So this way, we'll definitely have to stop. If I just run the program by itself, it prints 1, 2, 3, 4, 5, and not 0, 1, 2, 3, 4. Okay, the first value it prints is a 1 because it is a post increment. We use the 0 to compare, but by the time we get to printf, it's already 1. Okay, the increment is happening after the comparison, but before the printing. All right. So I know this looks like unnecessarily confusing, because why would we do something like that when we can just say x gets x plus 1, and why use post increment instead of pre increment and stuff like that? The answer will be clear when we get to arrays, okay? Because a lot of algorithms that we have to deal with use with arrays really benefits from post increment operation as a part of the condition. Okay, it shortens, it makes the code far more compact than the other form. But at this point, it's just a source of confusion with no particular reason. Are there any questions about this program? Questions? All right. So if there are no questions, I'm going to move on and talk about post-checking loop. This is a pre-checking loop because you can see that the condition is evaluated before we perform an action. A post-checking loop means the action is performed first, and then we use a condition to evaluate and decide, okay, should we go back and perform the action again, or should we get out of the loop? Okay, so that's what I call a post-checking loop. So let's move on to a post-checking loop. There's more stuff here. Basically it's just this part. Issues to be aware of. In general, the condition of a loop should mention at least one of the variables affected by the body of the loop. Okay, so getting back to the program here. While 7 is probably a better illustration of that. It's basically saying if you look at the condition of a loop, now this part does not apply only to pre-checking loop, it also applies to post-checking loop. You basically look at the condition that you depend on to decide whether I should continue or exit the loop. Whatever variable is mentioned here, at least one of those should be affected by the body of the loop. Now think of what happens when you have a situation where the condition, which is this one here, involves variables that are not touched by the body of the loop. Well, that means if the condition is true to begin with, it will remain true all the time because nobody is touching it. Is that making any sense? Then the loop becomes an infinite loop. Okay, somebody's going to say, but I learned how to write subroutines and I know about global variables. So I can call a subroutine inside a loop that calls a subroutine, and the subroutine changes that global variable that I use in the condition. So that way, I'm just kind of bypassing, everything. So, what I just said, is not true. Okay. Okay. Let me give you an example of that. So instead of doing this, if I make x a global variable, okay, let me illustrate that one. Okay. So I'm changing this program so I can make x a global variable. So if you declare a variable outside of a subroutine, it automatically becomes what we call a global variable. It becomes visible to the entire program. Okay, at least in this file, it becomes visible to the entire program. So that means I can write another subroutine. Let's just call it f here. And the only thing f does is to say, x gets x plus 1. Okay, this is a subroutine. I know the syntax looks kind of funky, but it's a subroutine called f, and the only thing it does is to increment the value of global variable x. So inside main, I can still do this, but if I do this, I'm not illustrating what a global variable would do. So I'm going to remove the local variable x here, change it back to 0, but instead of incrementing here, I would use function f to increment the value of variable x. So this time, it looks like, hey, TAC, look at this, okay? I'm using x to decide whether to get out of the loop or not, and yet in the body of the loop, I'm not doing anything to x. Look how smart I am. I can get around, the very same thing that you were talking about earlier. That is exactly why you should not use global variables. Okay. That's exactly why I would call global variables evil. Okay. Well, it is, because if you look at this program, you look at this program and go like, okay, it's going to be an infinite loop because nobody is touching x, global variable x, except subroutine f is touching it.
Well,
Okay.
it works out okay here because you can see it, but depending on how your systems are set up, you may not even really know where.
Yep.
Where your
Yep.
subroutine is called from.
Yep, exactly. The other problem is global variables are very tempting. A lot of times, you might have something in a program that it usually happens when you try to extend the ability of a program. It's like, okay, I want to add an option to this program. So if the user specifies this, I want the behavior of the program to do something other than what is already provided, okay? So what is the easiest way to make that user option visible to the rest of the program? A global variable. Okay, I set a global variable, the user specifies da 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 da. Okay, now the entire program knows about the user's choice, right? Well, it's very easy to make a global variable. You don't have to change the subroutines to use a global variable. But the moment you use a global variable, you lose the visibility of what a program or what your code is doing. Because when you look at line 13, does line 13 tell you that it might be changing global variable x? None at all. Okay, you can pass it by reference. Okay, in your previous class they should talk about passing by reference. You can pass x by reference to a subroutine, but at least it makes it clear. Okay, you are passing x by reference to a parameter to a subroutine. So as a result, it potentially can be changed by the subroutine. So it will still be clear to you and go like, oh, maybe it will change it. But this way is not obvious at all. Now think about this program being 50,000 lines, okay, which is a very small program by any scale, and has hundreds of global variables. Okay, it becomes a nightmare. Okay, it becomes a nightmare, even though someone can say, but all you have to do is to track down the subroutine and see whether the subroutine is changing or using any global variables. Then you can just track it down and figure out, whether a particular subroutine is doing anything. But what about the subroutines that the other subroutine is calling?
It's like jumping down a rabbit hole. You just start.
Yep.
That's a bad idea.
Yep. And they all start with one little thing. They all start with, oh, I just need a global variable so that I have a message to send from this part of the program to that part of the program. And the global variable is a little wormhole, right? It's easy, I just broadcast it to the other one. And then soon it will become unmanageable. Okay? So when you write programs, try not to use global variables at all. Okay, like 0 global variables. And you can write programs without using any global variables. It's just a matter of structuring your program in the right way and spending the time to think about it before you write it. Okay, so all of those things will become important. All right, so it's kind of like a go ahead.
So after that program is run, x is equal to 5?
You mean this one?
Yeah.
In this case, yes, x equals 5, when we get to the return statement. And in this case, x becomes a global variable and not a local anymore. I forgot to bring this earlier today, so the other 2 classes did not get the row sheet. Right. This statement is, don't worry if you don't understand what this means. This is referring back to if you use, a particular variable in the condition, then something in the code should change it, okay, in order for it to make sense. There are exceptions to that rule. The exception to the rule is when you have programs that are multi-threading, or interrupts are used. Okay, don't worry if you don't understand those terms. I just want to give you some early exposure of terms that you will encounter in the future. But there are exceptions to that rule that I just talked about. Yep.
Just for interest, in this course or in foreign?
Not in this class. These concepts typically will be in CISP 453 when we still offer that class, which is systems programming in Unix systems programming, which is kind of weird because that class is only required for transfer to Sac State, but not to UC Davis. And that's why that class usually don't get enough enrollment, and that's why we don't offer that class anymore. But these days, given the pool of students that we have, I think we have no problem filling that class. So if you want that class to be reinstated, you have to talk to Damon Antos. He's the
Oh, he's the head. Is that after assembly? Like, where is that fall?
Strictly speaking, it's after C. So
Anywhere
after cisp360, you should have enough knowledge to take that class. Yep. Right. The next topic is a do while loop, which is kind of like a post-checking loop. In the syntax looks kind of like a pre-checking loop, except it's different. It starts with a do, and then a particular statement to execute, and then the word while, and then a statement to specify when do I stay in the loop. In other words, when expression is true, we go back and perform whatever is specified here, then you go back and check expression. So you keep doing this until expression evaluates to false, then you get out of the loop. In other programming languages like Pascal and also in the pseudocode that I use in cisp300, I use repeat until instead of do while. There's only one minor difference, okay? When I use the word or words repeat until, that means whatever condition I specify after the until is the condition to get out of the loop, which is a normal use of the word until, right? You know, you can tell someone, you will keep doing this until all dishes are clean. So that means all dishes are clean is the exit condition, okay? When that condition is met, you can leave, okay? You don't have to do the dishes anymore. In this case, it is a stay in loop condition, okay? This expression specifies when do I keep doing this over and over again, okay? When this condition is true, we go back and perform whatever is specified, in this case, curly braces here. And that's it. That's the nature of a post-checking loop. Let's go through some sample programs just to make sure that we kind of understand how it works. So we'll have a do while 5.cpp, and we'll start with something that is pretty easy to understand and it's no big deal. Okay. So we will have do, and then inside here we have x gets x plus 1. We say while x is less than 5, return 0. And I think it can do it this way because I only got one thing to do in the loop here. Let me see if it is syntactically correct, because I think it is. Yep, okay. But even though this is syntactically correct, I would still use curly braces. Now in this case, it's not as bad as the other one, because if you try to insert another statement, you'll break the syntax. Okay, let me show you why I meant by that. Okay, you have to kind of think like a compiler in this case. Okay, so let's say we do have a global, not global, but we do have another variable y in this case. So y not existing is not a problem. So just kind of imagine that is the case. But if you are the compiler, then this is a problem, because you are only expecting one statement after the word do, but now instead of let me just highlight what I meant by that. So if you're the compiler, the first thing you do is you process the word do, okay, and that's indicative that this is the beginning of a post-checking loop, right? As a post-checking loop, you're expecting one single statement as the body of the loop. This is it. After that one single statement, after do, you're expecting the word while. And what am I getting here? Not while. So the compiler will complain here and say, hey, we got a problem, okay? I'm expecting the word while, and I'm seeing something other than while. Okay, the syntax is not right. Okay. Let's see whether G++ is really treating it this way. Okay, so this is do while 5, so I'm gonna rerun it, and it says right here on line 8, column 5, it says expected while before y, okay, which is exactly what I said. So in this case, the curly braces is not as necessary, because if you forget and you try to add something, between the statements, before the while, it's a syntax error. Okay, that you cannot just go, oh, okay, the program still compiles, but it doesn't do what you think it should be doing. But as a habit, I would still use curly braces, just so that we just make it a very consistent way of denoting the program. I know it takes up 2 extra lines, but it's not a big deal. All right, so let's take a look at this program. by the time we get to return, what would be the value of x? By the time we get to return 0, which is here, what do you think will be the value of x? It will still be 5, right? Because we cannot get out of the loop as long as x is still less than 5. But since it started off with a value of 0, and we only increment it by 1 with each iteration, so the first time we get to the while statement, x would have a value of the first time we get to x is less than 5. The first time we compare x to 5, what is the value of x? 1, exactly, because we have to perform the statement first. So by the time we compare, it already has a value of 1. So it will go from 1 to 2, 2 to 3, and then eventually it gets to 5. 5 is less than 5 is false, then we get out of the loop. So by the time we get to the return statement, it's going to have a value of 5. Okay. So this one, we can check it. It's not going to be very exciting. We already know what it is supposed to do. So we put a breakpoint on line 8. The only excitement of this particular debug session is when you single step from line 8, it doesn't go to line 10. Don't ask me why, because this has to do with how the debugger or how the compiler generates the line numbers, okay, as far as the symbol table is concerned. But when you single step, it actually does something really weird. It goes back to line 6, and at this point, it will evaluate the condition x is less than 5. Okay, I would say this is a bug, on the part of either the debugger or the G++ compiler, because it can be the G++ compiler emitting the wrong place for the debugger to track. Okay, but this is actually the while line. Okay, so when it says line 6, it really is on line 10. It is actually evaluating whether x is less than 5 or not. Okay. So the first time, it is not. Second time, it is not. Third time, it is not. Fourth time, it is not. This is the last time, okay? This is before the increment. X has a value of 4. After the increment, x has a value of 5. So even though it shows that we are on line 6, just think we are on line 10. Okay, let me just list the line numbers again. So we are actually on line 10 right now. It is evaluating whether x is less than 5 or not, okay? So when we single step, it would evaluate x is less than 5 is now false and get out of the loop onto line 11. So I just want to show you this, just so that when you debug your program using GDB or code blocks, because underneath code blocks it's really just GDB running, it might give you something kind of odd like this. Okay. All right, but this program otherwise is not really tricky. X ends up with a value of 5 by the time we get to the return statement. So nothing really tricky. So it's time to do something a little bit trickier. So I'm gonna write this as a do while. That was 5, so this one is 6. So I'm keeping pretty much the same program, except I'm going to change two things. Okay, so I will make this 5. I'll make this a equal to. Okay. So let's take a look at this code here. What do you think it's going to do? X is initialized to 5, and the condition of the loop to stay in the loop is now x is different from 5, not x is less than 5. So what do you think this program is going to do? Perform the same way?
Yeah, because we'll go through 0, well, 1, the first time we'll check, 2, 3, 4,
But isn't
and then
X
at 5,
X?
it will be equal.
But x started off with 5 already.
Oh, I didn't see that.
No, I
Yeah.
think it'll go through one iteration, and then it'll be raised to 6, and then it won't be equal to 5 anymore, and then we'll get to line 11.
So it won't be different. It'll be
Well,
different.
but when the condition is true, it goes back to do it again.
It'll be
The next becomes 7, 8, 9, 10. So none of those numbers will be equal to 5, right? So that's the first trick of this program is, wow, okay, it looks like an infinite loop, except it's not. Okay, so this is really tricky because I have two tricks combined into one little program, and one can quote unquote mask the other one. Okay, because one is it should be an infinite loop. The program should never ever get to the return statement. But when you run the program, it does get to the return statement. Okay, so first of all, let's go ahead and run this program. Okay, so we'll go ahead and g++-o do while 6 -g do while 6.cpp, and I'll run the program without the debugger. There really is no need to use the debugger at this point, and it feels like it's a infinite loop because the program doesn't seem to exit, right? Doesn't get to the return statement.
It's gonna roll back.
And then it got out. So how did it get out like this?
Because we have a finite set of bits, so eventually it's just gonna roll back.
It's gonna roll back, exactly. So that's why we have this little table here. Okay? But instead of using this, I'm gonna use a different representation because I think the other representation is even better. Okay. So given a fixed number of digits, okay, I don't even care what base we are dealing with, okay? Given a fixed number of digits, the numbers or the values that you can represent is fixed, limited. Does that make sense to you? Even with base 10 numbers, okay, if I give you 3 digits as a base 10 number, how many values can be represented? 1,000, okay? From 000 to 999, we have 1,000 individual values that can be represented by 3 digits. Is that making any sense? Okay, so regardless of even what base we're dealing with, the number of values that can be represented is fixed, okay? Now, with base 2 numbers, it's basically the same thing. Okay. So instead of looking the numbers as a number line, I look at a number circle because it wraps around. Okay. We start with 0. Okay. 0 is represented by the bit pattern 0, 0, 0, 0. We have 1 here, 0, 0, 0, 1. Okay. Nothing too surprising here. 0, 0, 1, 0 is the base 2 representation of 2, and eventually we'll get to 7 down here. 7 is represented by 0, 1, 1, 1. Okay? I mean, other than these are binary representations, there's nothing really too surprising here. Let's go to the negative side. This is -1. Does it make sense that -1 is on the other side of 0?
Yeah.
It makes sense. I mean, on one side you're adding 1, on the other side you're subtracting 1. So in this case, if you subtract 1 from 0, 0, 0, 0, you get 1, 1, 1, 1. Okay, that's just how the math works out. Okay, and then -2 is 1, 1, 1, 0. -3 is 1, 1, 0, 1, and so on. So eventually, it will get to this point, right next to the 7, right? Right next to 7, the binary representation is 1, 0, 0, 0. The value it is representing is -8. All right. Now this is called 2's complement, by the way. The way we represent negative values, but only using zeros and ones, is called 2's complement. In this class, I wouldn't worry too much about 2's complement, just because we are not going to get too much into 2's complement. The point is, it's a circle. So when you are adding 1. Okay, if you just imagine that you have a variable, okay? The variable is kind of like a fixed point here, okay? This is my variable x. Whatever this number is at this point is the value of x. This pointer does not move, but the wheel does. Okay, just imagine, Wheel of Fortune, and I'm not Vanna White. Okay, so when you're adding values, you're turning the wheel in a counterclockwise fashion. When you're subtracting 1, you're turning the wheel in a clockwise fashion. Is that making any sense so far? But since it's a wheel, eventually it gets back to the same point. You do this 16 times, it goes back to the same value. Now, it's only 16 because I'm dealing with a 4-bit number. When you're dealing with a program like this, x is a 32-bit number, which means you have a much bigger wheel. But nonetheless, it is not a number line, it is still a number wheel. It just takes a lot longer. It takes 4 billion clicks to get back to the same spot. What that also means is x, even though by the time you compare the first time, it has a value of 6, right? Does it make sense? Nope, 6. X is 0 to begin with, then you add 1 to it, it becomes 1. So by the time, oh, okay, that's the wrong code.
Since we initialized to 5.
You lost it.
There we go. So it was initialized to 5, then it gets incremented to 6. By the time we compare, this is already 6. 6 is different from 5 is obviously true. We go back, x becomes 7. 7 is different from 5. We go back to here, it becomes 8. 8 is different from 5. It kept going like this until it goes to 2 billion something. And then suddenly, one more increment, it flips all the way back to negative 2 billion something. Well, guess what? Negative 2 billion something is not equal to 5. So then it goes back and add 1. So it becomes negative 2 billion something plus 1, plus 2, plus 3, and then eventually it gets back to 0, 1, 2, 3, 4, and then 5. Then it exits. So this is a really, really tricky program because the first trick is to realize this is quote unquote an infinite loop. And then we go back and say, hold on a second here, it's not an infinite loop. Because of the way we represent numbers. You try to do something like this in Visual Basic, it will give you a runtime error. The moment you add 1 to it and you try to flip over to the negative side, Visual Basic will give you a runtime error because it basically says, okay, we have an overflow situation here. Okay, we're only using 32-bit to represent integers, and you are trying to do something that is not within the range of values that I can represent. So Visual Basic will actually give you a runtime error. C does not. C and C++ trusts you.
Yeah, that's a bad idea.
I think you know what you're doing. I'm not going to say anything. And this is only one of the minor cases where it would say, okay, I think you know what you're doing. I'm not going to say anything. Okay, there are many, many other situations far worse than this that it would use the same type of philosophy. Okay, but getting back to that topic, there's one reason why C does not do any type of range checking, to detect things are getting out of range. It's for efficiency. Because in order for a program to detect, oh, guess what? If you add 1 to this number, you're going to exceed what you can represent using a 32-bit number. That requires a comparison and a check. Which also means every time you perform the statement x gets x plus 1, there's an implicit check associated with that increment. And that takes extra time. It makes your program run slower. That is the primary reason why C and C++ does not do any type of checking. It just gives you, if you say this, I'm going to do that. Okay, you are responsible to make sure the number stays within the range that the number can represent. So keep that in mind, not only in this class, but every time you program in C and C++, keep that in mind, that the language trusts you to know what you're doing. It doesn't do a lot of extra checking, even if you ask it to. All right. Any questions about this program? Why it is doubly tricky?
How long does it take for you to go from one range to the other?
Say again?
How long does it take to
It depends on the processor. It depends on the program. In this case, it didn't take very long, did it? I mean, it took a couple of seconds, but that's actually a pretty long amount of time already. These processors run at 2.3 gigahertz, and ideally speaking, it can perform 1 addition per clock, which means it can actually perform like 2 billion something additions per second. But now, since it cannot do that because we have a variable that lives in memory, so it's basically limited by how fast it can access memory to keep it updated. Even the cache is not like quote-unquote real-time. It cannot be as fast as registers. So that's why it took a couple of seconds. In fact, we can find out exactly how long it took for this program to... There's a command called time in Linux, Unix actually in general. And what it does is it will keep track of how much execution time it takes for a program to run. So in this case, we can run it, and when it comes back, it will show you how much time it took.
Will it print it nicely or like in milliseconds or?
It prints it in a way that we can read, so 8 seconds or so, okay, 7 or 8 seconds, which is probably about the right range, given that we have to at least, every time you store something into memory, it takes longer than doing it in cache. So that's about the right, range of values. All right. So are there any questions about this particular program using post checking? No questions? Okay. Right. So issues to be aware of: as a post checking loop, a do while loop performs at least one iteration. Okay, so that's the part that is important. Is you perform an iteration regardless of the condition. Then you check the condition. So you got to keep that in mind. So code between the curly braces in the template right here executes at least once. So in general, pre-checking loops are used much more often than post-checking loops. So just kind of keep that in mind. It's really kind of rare that we have to use post-checking loops, because for the most part, you usually have the condition to check first, and then you decide whether you have something to do when the condition is true. The only time you use a post-checking loop is when the condition itself is affected by what you do here. Okay, that is pretty much the only time when you need to use a post-checking loop instead of a pre-checking loop. All right. Any questions about the concept of a post-checking loop? No questions. Right. If there are no questions, we'll move on to the concept of a for loop. A for loop is essentially a shorthand of a particular type of while loop. Okay, so it's nothing new. It's just rearranging things a little bit differently to make certain things more clear than otherwise. That's basically the whole idea of a for loop in C and C++. The syntax of a for loop is like this. Okay, it has a for keyword, so you have to type FOR. Then you have a parentheses, a pair of parentheses here. But what's inside the parentheses are 3 individual items. You have one init expression, you have one expression to say when to stay in the loop and when to exit the loop, and you have one expression to say what to do when the body is done. Okay, so what I'll do, instead of just explaining that, I'll just refer to something that we have just talked about. This loop here is identical in terms of what it does with that one here. In other words, the initialization expression is just something that you do before you get into the loop. That's why it's called initialization. You're doing it before you get to the loop. The expression is still the same place. Okay, this expression is the same one here. While the expression is true, we perform the loop body. What is kind of weird is the post. Post is the post operation of an iteration. So if I were to write it as a for loop, I would put it here. But if I convert the for loop into a while loop, I would put post all the way down there. It's basically stuff that you do at the end of each iteration before you go back to reevaluate the expression. EXPR. Are we doing okay so far with looking at this and say, oh, okay, so I can see it's really just a while loop. Okay, no questions. Okay, let's do one example with this. Go ahead and write for, I think we'll do 4, 5 here, and to make this make any sense, I'm going to use 2 integers, in this case 2 variables. So x starts with the value of 0, y starts with the value of 100 and then we'll first write it as a while loop first. Okay, then we'll rewrite it as a for loop. Okay. So as a while loop, this is the initialization, and then the condition is, let's say while x is less than 5, we stay in the loop here. And the only thing I really want to do is to print the values of x and y. don't worry about this part. We will talk about the printf and how we format the output of a printf later on. But what this really does is to print the value of x and y to the output of this program, and that's all it's going to do. And then after this, we get x gets x plus 1, y gets y minus 1, and return 0. Okay. So based on what we have talked about already in today's class about a pre-checking loop, we kind of know what this program is going to do, right? How many times is it going to go through the main body of the loop? Exactly 5 times. And the value of x goes from 0 to 4, stay in the loop, because when it gets to 5, we get out of the loop. Then the second thing is y starts with a value of 100. It decrements for each iteration, so it will print 100, 99, 98, 97, and 96 for y, and then for y, and then for x it will go from 0 to 4. Okay, so we'll go ahead and run this program just to be sure that's exactly what this program is going to do. G++-E-O 4545.cpp. Okay, kind of what we expected. Are there any questions at this point about this program? And remember, we will talk about the printf, kind of cryptic line, later on. But for the time being, all we really care is, it's going to print the values. It will print the values of x and y. Any questions about this program up to this point? Okay, nothing too surprising. So what we'll do is I'll copy this program to 4.6. So 4.5 becomes 4.6. And then we'll edit both. We'll look at one program on one side and then change the other program on the other side. And this is one thing I really like about VI is we can split the screen, so it's easy to look at 2 programs at the same time, especially when they're related. Okay, so if I turn this into a for loop, I will take away some of the. Oops, that one I don't want to take away. So I'm going to leave this part as the body of the for loop, and then I'll use for semicolon here, and then specify the content in the for loop. The initialization is x gets 0 and y gets 100. So in this case, x gets 0 and y gets 100 becomes the sub-expressions of a comma-separated expression. Remember, I can only have one expression for initialization, but that's okay because I can use a comma to combine multiple expressions into one. So it is still counted as one expression even though it has 2 assignment operations in it. Is that okay? When it is separated by commas, it is not a statement, it is an expression. The condition still go to the same spot, which is here, x is less than 5. And then the post operation is x gets x plus 1, y gets y minus 1. You know what? I'm just going to use these operators instead. Increment x, decrement y. Now, in this particular context, whether I use plus plus x or x plus plus makes absolutely no difference. Because nobody cares about the value of the expression. The only thing we want out of plus plus x or x plus plus is that x gets incremented. But what the expression returns is of no value to me at all. And that's why whether you use plus plus x or x plus plus makes no difference. Are there any questions about this code here? All right, so what we'll do next is to run the second program, make sure that it does what the first program does, and then we'll go back to it and then kind of re-examine why is this any better, okay? Is it any better? And if so, why is it any better? So G++-G-O 4646.cpp. And it works exactly the same way, okay? There's literally no difference whatsoever compared to the first one. So why bother? Okay, yeah, it's a little bit shorter, but for the most part, the length of your code really doesn't matter. The one thing that it brings to the table is it concentrates everything onto the same line. Okay, the initialization, the condition to stay in the loop, and the post operation. They are now all right next to each other. And this is a good thing because all of these things, all of these items are related. Okay, the condition that determines whether you stay in the loop or whether you exit, along with the initialization of the variables involved in that condition, as well as the post operation involving the variables involved, they are now on the same line. So it makes it clearer of what you need to do to prepare for the loop, what you check for each iteration, and what you do after the operation of each iteration. So it brings everything into the same line, so visually they are closer instead of having the other way, which is spread all over the place, right? This is the initialization, this is the condition, and the worst part is what we do after each iteration. Now this is a very simple loop, and that's why you might not see the advantage, but if you have a loop that has, let's say, 60 lines, that will push the post operation onto the next page. So it becomes less visible to you, what you're doing for each iteration that will change the condition that you eventually will use to exit the loop. But this makes it very clear. That is the value of a for loop. It doesn't do anything other than, moving things around, to make it more clear. But other than that, you can live without a for loop. It's not a big deal. Any questions at this point? No questions? All right. So if there are no questions, I'm going to admit to a omission on my part. Okay. I should have another slide here or another document here to talk about lazy evaluation, otherwise known as short-circuited evaluation. Okay, because this really is a good spot to talk about it when we have loops to talk about. Okay, so what I'll do is I'm going to show you a program, and you can tell me what it does. So this one is going to print something to the screen. All right, so we have two variables, x and y. And we'll initialize x to 0, y to 100. So this resembles one of the other programs that we have written up. That I have written up to this point, except the condition is a compound, is a conjunction. So I'm going to keep x is less than 5 here, but I make it a conjunction and say, well, y post decrement, we want it to be greater than 0 in order to stay in the loop. And in the loop here, we have the usual printf. X is %d, y is %d. The %d is basically a placeholder, and then you supply the values to specify each placeholder and say, okay, that placeholder is supposed to be x, the other placeholder is supposed to be y. And then after this, we have x gets x plus 1, and now we have a return 0. All right. So for the most part, this code looks very similar to the previous program, right? There are two things that are different. One is I don't have y gets y minus 1 in the loop body itself. Instead, I use y minus minus as a post-decrement operator inside the condition itself. So that's one difference. The second difference is the use of a conjunction here. Okay? In the previous program, I just rely on the value of x to determine whether to stay in the loop or exit. And this time, I'm using x and also y to make that determination. Most people look at this program and they can immediately tell and say, don't bother. I mean, this is, y is always going to be greater than 0 because x will get to 5 way before y even gets close to 0, right? X is 0, 1, 2, 3, 4, 5. Okay, time to exit. Y has to start from 100. Okay, 100, 99, 98. It's going to take a lot longer to get down to 0. So it seems like the second condition is, is pointless to have it there. But now the question is, what do you think this program is really going to print? And by the time we get to the return statement, what is the value of y? Okay, so there are two questions that I want you guys to answer. Let me repeat that again. what is it printing? Because it's not going to print the same thing as last time. And 2, what is the value of y when we get to the return statement? Okay, let's answer one question at a time. What is it going to print? The initial condition is x is 0 to begin with, y is 100 to begin with. Okay, 0 is less than 5, no problem, that is true. Y post decrement is greater than 0. Now, when we have a post decrement, it means I am using the value of y prior to the decrement to compare to 0. Most people say that, wow, 100 versus 99, they're both way more than 0. Why do I care? Well, you do care because when we get to the print line, the printf line, the value of y is different from last time. Okay, so let's take a look at this one here. Y started off with a value of 100 from the initialization. So when we compare to 0, we are actually comparing 100 to 0. 100 is greater than 0. Woohoo, big deal. But remember, this is a post decrement, which means I'm also having a side effect of changing y to 99 when we evaluate this part here. So by the time we get to the printf, y is no longer 100, it is 99. So the first line this should print is x equals to 0, y equals to 99, not 100. Is that okay? Okay, how many times are we going to print? 5 times, because x is going to run out first. Okay, y still has ways to go before it can trigger the other condition to be false. Okay, so the first line would print 0, x equals to 0, y equals to 99. Second line is x equals to 1, y equals to 98, and so on. And it will print 5 lines. Okay? So when it prints, y goes from 99 to 98 to 97, 96, and then 95. Y equals to 95 is the last line that's going to print. So the next question is, by the time we get to the return statement, what is going to be the value of y? Most people would say, you tried to trick me again, right? Because it's a post-decrement operation, so it's going to be 94, because we will still do the comparison one last time, and by the time we get out, y minus minus will still happen, and so y will now be 94. Well, if it were like that, I wouldn't call this extra tricky, right? So the reason why I call this extra tricky is because y ends up with a value of 95 by the time we get to that return statement. It all has to do with lazy or short-circuited evaluation of a conjunction. Okay, so let's think from the perspective of a really lazy person. Okay, such as myself. Okay, so let's just say that this is the last iteration. After the last iteration, x ends up with the value of 5, and y ends up with the value of 95. Okay, we know that much already. So x is 5, y is 95. So when we get back to this condition here, you say x is 5, 5 is less than 5 is false. Right? But this is a conjunction. Now with any conjunction, if at least one side is false, the entire thing is false. So if I were a lazy, really lazy person, or computer, or program, I'm going to say, the left-hand side is false, I don't even bother with the right-hand side. But if I don't do the right-hand side, y minus minus never executes. And y remains a value of 95 and never gets a chance to decrement. Is that making any sense? It's a little bit tricky, right? Okay. So the next question is, let's just say that the compiler will try to generate code that is as lazy as possible. But conjunction, by its very nature as a mathematical operation, is commutative, which means A and B is the same thing as B and A, just like multiplication. Okay, it shouldn't matter which side is evaluated first. So in this case, what guarantees that we will evaluate the left-hand side first, and then use that to decide whether we even bother with the right-hand side, because it could easily just go to the right-hand side first and then use that to decide whether we evaluate the left-hand side. Is that making any sense?
The compiler will do that, like the way that it turns that code into object code.
Right.
Or you say that.
Yeah. All I'm saying is, to a mathematician, the order does not matter.
Oh yeah.
To a mathematician, they would go like, okay, well, but no one is going to stop me from evaluating the right-hand side first, and then use it to evaluate to determine whether the other side needs to execute. Well, the answer is actually pretty simple. The ISO C++ standard dictates that when you have a conjunction like this, it always evaluates from left to right, and then use the lazy evaluation in the process. Okay, that is a part of the language specification. So there's no confusion. When you see something like this, it has to evaluate from left to right, and then it will quit as soon as possible. As soon as the conclusion is done, it doesn't evaluate any further. Okay. Now let's go ahead and run this program, through the debugger, just to make sure that everything that I said is true. You will never hear a politician say that. No politician will say, "Do not trust me."
Yeah, but they also never really give you a straight answer either. So it's kind of like they never give you a straight answer either.
Well, sometimes I don't either, but I want you guys to think about it, right? It's the combination of saying "Don't trust me" first. That reminds me of a really old TV show. It's called Sledgehammer. Many of you are way too young to have watched that show. It only went on for a few seasons, and then they had a police brutality case, and then that show had to be canceled.
That makes sense.
Yeah, you have to watch it like a few times, then you understand why police brutality might end that show prematurely. But the catchphrase of a Sledgehammer what is his name? His actual name, in the character's name. But one of his catchphrases is, "Trust me, I know what I'm doing." And then that's, of course, his famous last words. Okay, so I'm going to put a breakpoint on line 14, because we want to know, what is the value of y when we get to line 14. And then we'll just run the program at full speed, because it will just print a few things. So as expected, it prints, x goes from 0 to 4, y goes from 99 to 95. So that part is kind of expected. But the last one is, what is the terminating value of y? It's 95, not 94. And that one is because of lazy or short-circuited evaluation of the conjunction. So are there any questions about this particular sample program? Yep.
If we wanted 94, couldn't we just switch the y expression in front of the x?
You can always do y gets y minus 1 after line 12,
No,
instead of
line
using
9.
y minus minus.
On line 9, can we just do y minus minus greater than 0 and x minus 5? Switch the two value, the expression?
Yeah, that would do it.
Yeah.
Yep. Because in that case, y minus minus is greater than 0 is always true. So it always has a need to evaluate the other side. Right. Yep. So that means switching the order is important. Now, once again, people might ask, but why do we have to deal with something like this? I mean, it doesn't seem to make a lot of sense. It causes a lot of confusion. When we get to arrays, it will be clear. Okay, all of these things, lazy evaluation, using post-increment or post-decrement in the condition of a loop, all of these things will basically make certain types of code look really, really clean and short when we get to arrays. Okay, so you just kind of have to hang on for a little bit longer until we get to arrays. Then it will be clear why we have all these kind of odd features. I'll see you guys on next Monday. Have a nice weekend, because there's no class on Wednesday. I won't be here on Wednesday. It's kind of odd to say, have a nice weekend when it's only Monday. Sorry?
I said I wish it was like that for the rest of my classes. But so, question:
But then you won't be getting your money's worth.
Oh, absolutely, absolutely.